we'll start recording. It's July 6th, 2017. We had left off talking about the limit, and so we had said that the limit. Red is just such a non-peaceful color. The limit is x goes to a of f of x is equal to L if. So this is not the official definition. This is how we write it in words. If f of x can be made, and I may have used a different word yesterday. I prefer this word, arbitrarily close to L by making x sufficiently close to A. Right, so here's an example. The limit as x tends to 3 of x plus 5. Okay. So in this case, the function in this case is x plus 5. The claim is that this number is, what is it? 8. Thank you. Appreciate that, brother. Limit is x goes to 3 of x plus 5 is 8. That's a claim. And so the way we would go about proving this is that we would say, oh, that's outrageous. We would say that as we can make x plus 5 very, very close to 8, as close as we want to 8 by taking x close enough to 3, right? And so so what does close mean? It means that we're looking at x plus 5 minus 8. And what do we want to say about that? All right, so wait, what is this? This is the absolute value, right? So the absolute value of the difference is the same thing as the what? It's the distance between these two, right? So let's say this clear. This is the distance between x plus 5 and 8. Right? And the question is, can I make this as small as I want by picking x as close to 3 as I need to? And so what is x plus 5 minus 8?
X minus 3.
It is x minus 3. Right, so that equals x minus 3. And the question is, can I make this as small as I want by picking x as close as I need to 3? The answer to that is yes. Let's just pick, let's take some examples. So the great skeptic comes in and says, yo, I don't believe this goes to 8. Right? And so the great skeptic says, I think it stays away from 8. And then you say, well, look, you tell her that the difference is, well, I'm going to measure the distance by taking the absolute value of the difference. And she says, that's perfectly okay. And then you say, well, that's x minus 3. And she says, yeah, that's okay too. And then we say, well, you think the distance is bigger than something, right? Because if you didn't, then you would think that they get closer to each other. And she says, yes, that's right. And then you say, well, what do you think it's bigger than? And she says, I think it's bigger than 0.001. And then you say, well, wait, so you think it's bigger than 0.001 no matter how close I take x to 3? And she says, that's right. And I say, prepare to lose, right? Because if x is equal to what? 2.99999, then the absolute value of x minus 3 is equal to 2.99999 minus 3, which is equal to 0.000001, which is certainly less than 0.001. And so she's wrong. And then every time she picks a number, you can pick a value x that's close enough to 3 that proves her wrong. And you can do that for every value she gives. And so what Weierstrass was able to say is that for every, and I'm not going to test you on this, this is for math majors, but for every epsilon greater than 0, there is a delta greater than 0 such that the absolute value of f of x minus L can be made less than epsilon if the absolute value of x minus A is less than delta. I'll never write that again, but that is the definition. Okay, so this is good. From now on, stuff in green is optional. We'll leave that as the case. So all that means, again, in words, is that when the skeptic says, can you get this close? Then you can by making x close enough to A. I can make f as close to L as I want, the distance from F to L as small as I want by finding an x close enough to A. That's what it means. Please. Oh, thank you. All right, so at best, that's a extra credit type thing. That's a bonus thing that I would put on the test. Can you write the exact definition of the limit? 10 points or something like that. Okay. What I'm going to be asking on the test, though, is the wording that you can make. We would be convinced that the limit as x goes to A if f of x is equal to L if you can make f arbitrarily close to L by picking x to be sufficiently close to A. Those are the words. Yeah.
Yesterday you said sufficiently twice. Can we use that too? Like,
I prefer arbitrarily.
Okay.
Yeah. Arbitrarily for the first word. So I can make f as close to L as I want. That's an arbitrarily close thing. Does that answer your question? We open the... Miss?
Yeah.
That answer? Okay. Excellent. 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 Scroll. Oh, more all the way to the top. Thank you. Yeah. So yeah, this is the downside to having this one screen. Everyone shares it, as opposed to this place is ridiculous. There's a board in one of these rooms that has that goes all the way up to the ceiling. It's got 3 of these. Yeah, the board's all around the room, right? So, but here we have this one screen. Today I wanted to talk about 3 things. I wanted to talk about limits, I wanted to talk about continuity, and then I wanted to talk about the homework. Okay. Questions about this? Are we good now? Yes.
Scroll down.
I can, absolutely.
Is the test going to be next week?
I'm sorry?
The test will be next week?
Oh, absolutely not. So I don't think we'll get to the end of chapter 2 by next week. We are not. We cannot go that fast. My conscience will not allow that. That's crazy. Yeah, because then it doesn't allow. Because again, we're looking for depth. So again, this is a difficult navigation between depth and speed, right? There's material to go through, but we want to go through it so that we're understanding it. So it's a balance. Are we good here with this page? All right, so we had made the argument of talking about the limit from the left and the limit from the right. Let me add a page. So we had said the last thing we wrote basically was that and I've got to change colors here, I'm sorry.
Thank you.
So much nicer. The limit as x goes to a from the right of f of x is equal to L, and the limit as x goes to a from the left of f of x is equal to m, right? We defined those things. Those were the last things that we defined on last class, right? And this was that you can make the function arbitrarily close to L by taking values of x arbitrarily close to a but bigger. Here you can make f arbitrarily close to m by taking values of x that are close to a but smaller than a. That was the last thing we said. Here we've got one such function. Here is the function when x is less than 0, I want the function to be x squared. This is clearly the parabola. And then when x is greater than or equal to 0, I want the function to be x plus 1, piecewise function. Of course, what we're interested in, I guess I can take this, we're interested in the limit as x goes to 0. So, oh, actually, I should be able to do this, right? Be good. No, you're not being good. Okay. So then we're interested in the limit. Here's f of x. And so in test form, it's going to be written like this. It's x squared if x is less than 0, and it's x plus 1 if x is greater than or equal to 0. F of 0 is 0 plus 1, which is equal to 1. 0, this 0 here corresponds to the fact that that condition here, x is greater than or equal to 0, so 0 belongs to the second branch of this function. F of 0 is 1. The limit, I don't know how I get back to red, it's so subconscious. The limit as x tends to 0 from the right of f of x is asking what happens when I'm on the function. Now remember, f represents the y value. Y equals f of x. And so we're asking what happens to the y values when the x values approach 0 from the right. So that means you're looking at the y values. Here are the y values. And from the right, it looks like it's
approaching 1.
Approaching 1. That's right. And so it looks like it's approaching 1, so we say that the limit is equal to 1, right? And similarly, the limit from the left from this thing. Right, so people last night were able to do this pretty easily. This is equal to the limit as x tends to 0 from the left of x squared, right? And so for values of x that are less than 0, that's on this branch, and that is 0. The limit as x tends to 0 of f of x is does not exist, right? The reason is because we want the limit to be one number, and so there is no one number that this approaches as x tends to 0. And again, the way that you would prove that, of course, is the great skeptic will come in and say that, yo, there is a limit. And you say, no, there isn't. And then he says, well, prove it. And I say, well, you think there is one? Right? And then he says, yes. And you say, so you think there's one number that this function will approach the closer you get to 0? And he says yes. And then you simply say, well, it looks like that when I look at 0.01, 0.0001, 0.00000001, right, then it looks like that you're getting closer and closer to 1. And then he says yes. And I say, well, wait, if you do negative 0.01, negative 0.000001, it looks like you're getting close to 0. And then he says, oh, right. So if there were one number that this was getting closer and closer to, then that means that if you were to take any interval around 0, then all the numbers in this interval should be giving you y values that are close to one number, and clearly that is not the case. So the limit should be unique. And so the theorem that we had last time that we mentioned is an if and only if, and it says that the limit as x goes to a of f of x is equal to L if and only if the limit as x goes to a from the right is equal to the limit as x goes to a from the left, and they both have to equal what? L. So what do I mean by if and only if? It means that if you start with 1, the other one happens. So there are two statements here. This is statement 1, and this is statement 2, right? And if statement 1 is true, then statement 2 is true. And if statement 2 is true, then statement 1 is true. That's what we mean by if and only if. That if you start with this, then this has to follow. If you start with this, then this has to follow. The negation of this is also the case that if the limit as x, if the limit does not exist, then that means that the left-hand limit and the right-hand limit could not be equal. If the left-hand limit and the right-hand limit are not equal, then there is no limit, right? So they just go together the whole way. If one is true, the other is true. If one is false, the other one's false. I'm going to go back and fix this. Of course. Are you going to let me edit this? There we go. Is there a limit at 0?
Yes.
Okay, so let's prove that. Show that f of x equal to x squared if x is less than 0, and x if x is greater than or equal to 0 has a limit at x equals 0. From the theorem that we just showed, we simply need to take the limit from the left, take the limit from the right, and show that they are equal. So for piecewise functions, that's usually what you do in order to show that a limit exists. The limit as x goes to 0 from the right, and the limit as x goes to 0 from the left. All right, we're going to show that they're equal. As we go through some of these problems today, I'm going to talk to you about my third alter ego, and that is Grader Winger, Grader. The grader wants to see, the grader is a mathematician and wants to see preciseness. So you'll see me write limit every single time until it's time for me not to use it, until I apply it. The limit as x goes to 0 from the right of f of x is equal to the limit as x goes to 0 from the right of, so from the right we're talking about, lost my cursor, it's right here, it's this branch of x, which is 0. The limit as x goes to 0 from the left of f of x is equal to the limit as x goes to 0 from the left of x squared, which is also 0. So since these are equal, the limit as x goes to 0 of f of x exists, and it's also equal to 0. Questions there about that, about how that's written? Again, so on the test, and this is true in general, on the test for the rest of your educational careers, you should always assume that you have the hardest grader in the world. Last year, I had some wonderful conversations with your predecessors in this program. I gave the first test in this class, and then I graded it. Grader Winger graded it, and then people came to me after the class and said, "Well, wait, why is this wrong?" And I said, "Well, how would you do this?" And then the person said, "Well, you would do A, B, C, D, and E." And I said, show me where that is on the paper, Claire. She says, "Well, I thought you knew I knew." I thought you knew that I knew that. Like, who are you talking? What? Right? So on the test, write so that I know that you know, right? So yeah, there should be no conclusion about this. This is perfect, and then I know, oh my goodness, I feel speed demons in the room, right? People who just like to race through stuff as quickly as possible, right? So and so some people are going to say, well, can we skip this step? Can we not write this? Can we go skip whatever you like? Just be right. Skip whatever you like. Just be right, please.
So we're just gonna find like f of this, like in homework, we must write like limit every time.
This is a good question. What would you write instead?
I kind of like simplify the equation and then we're limit and simplify.
Yeah, I would need to see it. I would need to see it. It's up for debate, right? So this, that's wrong. Like this is just wrong. Okay. So yeah. I mean, this doesn't even make any sense. Okay. So please.
So if you want us to write the limit of f of x first, then substitute it in, or can we go back to the limit?
So you just want to start here.
Yeah. You want us to write that f of x.
This is fine. I want to be clear that so this is probably going to be, I'm being just so truthful, right? So depends on the mood on the day, right? So 90% of the time it's fine, but it's perfectly fine if you just happen to write these extra few things. I'm sorry to inconvenience you, but yeah. So again, writing this, what do I know? Let's be clear about this. Writing this, what is the writer telling me when they do this, when they write this?
That they're considering both sides.
Yes, which is precisely what I would like to see, right? When I ask you to show this, I don't give a damn whether you can plug in 0 into x or x squared. I need to know whether you know that we're considering the limit. You want to know about the limit from the right and from the left. That's what this problem is about, not about whether you can do the algebra, right? So again, I'm looking for, and obviously I would love if you say, in order to do this in words, in order to do this, you need to consider the limit from the left and from the right. That's just like a mathgasm, right? That's just fantastic for me, right? So again, or for the grader, right? So yeah, write so that the grader cannot mark anything wrong, on the test at least. Now, Jessica is an angel, so she's going to be fine, but the grader is not. Okay. Other questions about this? I'm going to consider other limits. There was a problem, something like this. Oh, so let's do something like this. So g of x is equal to, let's do 4x plus 3 if x is less than, oh, this is perfect. X is less than or equal to 0. And then we want it to be ax plus 6 if x is bigger than 0. Right, so So 4x plus 3, ax plus 6. Um, 4x plus 3, ax plus 6. I want to slide a, and oh my goodness, this Desmos is out of control, right? The question is, what should a be? Oh, you're not going to let me do this? Yeah, so that the limit exists. What should a be so that the limit exists? Can it be anything, right? So let me maybe it can be anything. Let's do that. Actually, no, I want to do this. I do want to do this. Let's do 3x plus a. A should go inside. Let's go ahead and show that it looks like it's that, right? Whatever that is. Is that 3?
Yeah.
Okay. Please, go ahead.
For the equation on the board, it was x is less than or equal to 0, but on the calculating, you have the opposite way, so I'm just trying to.
Oh, let's take a look. Less than equal to? Okay, I can put the equal to here. As you might know, it's not that big of a deal. Thank you. So it looks like A should be about 3 for this to work. Something like that to make things fit, right? Let's go ahead and demonstrate that. Why is it 3? Well, we need the limit from the left to be equal to the limit from the right. So the question is, what value of A makes the limit exist? What value of A makes the limit as x goes to 0 of g of x exist? We'll do this. And there are a couple of these on the homework. So in order to find this, we need an equation. Obviously, we're looking for A. We need an equation to solve for A. That equation comes up from the fact that if we want the limit to exist, the limit from the left needs to be equal to equation the limit from the right. So the limit from the left as x goes to 0 from the right of g of x needs to be equal to the limit as x goes to 0 from the left of g of x. And we're going to calculate each one of those. I want probably to change this number to something else, but oh, actually no, this is okay. I think. Wait. Oh, I changed this, right? So
Yeah, it was 3x plus a.
The limit from the left, let's do the limit from the right. The limit as x goes to a, x goes to 0 from the right of g of x is equal to the limit as x goes to 0 from the right of 4x plus 3. Which is equal to 3. The limit as x tends to 0 from the left of g of x is equal to, let's make sure that's right. It's the other way around, right? 3x plus a. 3x plus a. Plugging in 0 for x, that's a. The limit from the left as x, the limit as x goes to 0 from the left of g of x is equal to the limit as x goes to 0 from the left of 4x plus 3. That is equal to 3, and of course we need these to be equal. So that's why it needs to be 3. Questions about that? So yeah, this would be phrased in all sorts of different ways, but the remark is the same, right? Take the limit from the left, the limit from the right, plug it in, and you're supposed to get the same thing. All right, so that's a classic one. Let's talk about other funky limits. I'll take questions on this though. Please.
Why did you set it equal to A?
That's a great question. So the goal of this problem is, what should A be for the limit to exist, right? What should A be so that the limit from the left equals the limit from the right? Here is the limit from the right. Here's the limit from the left. If the limit is to exist, I need those two limits to be equal. Is that okay? So the limit from the right was A, and the limit from the left was 3. And so if the limits to exist, they need to be set equal to each other. Is that okay? And so A is 3. Thank you for your question. Other questions about this? Okay. Technicalities about these other limits. There are all sorts of funky ways of talking about limits. We got to talk about other limits. So these are infinite limits. And so when we say the limit as x goes to a of f of x is equal to infinity, what does that mean?
It means that
Classic example. 1 over x squared. That thing right there. The limit as x goes to 0 of this function is infinity. Why? Well, certainly that's what we're going to define the asymptote to be, right? So that now in pre-calculus we talk about vertical asymptotes, and now we're going to give the calculus version of saying that. So a vertical asymptote is going to be a vertical line that has a property that has to do with limits. Okay. So we can't use that to be the reason, right? Because that's going to be like a definition. Okay. Why is this infinite? As you might expect. Oh, go ahead.
As x approaches 0, y becomes infinite.
Say it again.
As x approaches 0, y becomes
To infinite, right? And so right now, at this point, we don't have a notion. We don't know what that means. We're trying to define that, right? So what you just said, we're trying to explain what that means, right? So in the Weierstrass context, think about the skeptic. What is the skeptic going to come and say? No. What is the skeptic's not going to believe us, right? The skeptic is going to say, I don't believe it gets higher and higher, so I think it stays under some number. And then, of course, we're just going to break him down, He's going to say that I think it stays under this number, M. right? I think it stays under 1,000. And then what do? You take an x close enough to 0 that goes above 1,000. And then he says, no, wait. I think it's 1,000,000. And then you pick an x close enough to 0 that goes above this. For any m, you can find an x close enough to 0 that's bigger than what? That's bigger than m. Every time somebody gives you an m, you can find an x close enough to 0 that's bigger than m. And so all that means is that when you graph, that never works. When you graph y equals 100, there it is. Wow, so this doesn't even go above 100, does it? Well,
What's the adjustment in the SAMS?
oh, right. You just need to go up high enough, right? So
Zoom out.
I can zoom out.
Yeah, on the right side.
If you go to settings, you can like adjust the y-axis.
I can. And so we can look at the table, right?
Like the settings on the right.
Right. So we say at 0 it's undefined, right? But then when the skeptic says, well, I don't think it goes above 100, then it goes above that, right? What number is that? 10 to the 8th? 100 million, right? 8 zeros, right? And then the great skeptic says, well, I don't think it goes above 10 trillion. And then you just need to add some zeros, right? For any m, you can find an x close enough to 0 that goes above that m. That means it goes higher and higher and higher. That's the definition. Okay. Means, in words, this means that f of x can be made arbitrarily large by making x sufficiently close to a. And so for my few math majors, that means that for every m, there is a delta such that f of x is bigger than m whenever the distance from x to a is less than delta. All right, so the stuff in greens for my future math majors, the stuff in blue is for us in words. You can tell somebody that on the street, they will understand it. The stuff in green is what the math majors will need to master. Right? And so again, it's saying the same thing. You pick an m, I can get bigger than your m. For any m, right? That's what we mean by infinity. That it just gets bigger and bigger and bigger without bound. And the way that we say that in English is that you can make this arbitrarily large as you want. Right? Questions about that? So the pre-calculus definition is that, and again, what I want you to do probably is I want you to think about, let's say in words, I'm not going to write it out, but let's say in words what this means. The limit as x tends to a of f of x is equal to negative infinity. Oh, you want me to zoom back up?
No, I just have a question.
Yeah, go ahead.
Your notation, it's not. But, I thought that the triangle was delta. Are there like?
Oh, this is a Greek letter. Yes.
Okay.
So yeah. So
wondering.
in mathematics, we use Greek letters a lot.
Okay.
So that's the Greek letter for delta.
Thank
Yeah.
you.
Yeah. No, not a problem. I'm sorry.
What is that? Okay.
It's a
The,
lowercase dude.
This here? Oh, we still call that delta.
oh.
Yeah, we still call it. Yeah. Yeah. So I don't want to Thankfully, no one's in a sorority yet. So delta sigma theta is serious, I understand. So yeah, but the Greek letter for delta is that. Um, what would we say about this one? The limit as x goes to a if f of x is negative infinity. This means that for any m, I can make f of x what relationship to m? Less than m. For any negative m, I can make f of x less than m by making x sufficiently close to a. And so the definition of a vertical asymptote is this. X equals a is a vertical asymptote if the limit as x goes to a of f of x is infinity, or the limit as x goes to a of f of x is negative infinity. Some people like to be lazy and say if the limit is x, I'm sorry, I'm going to scroll this up. Some people like to be lazy and put plus or minus infinity. I probably will do that as well, but for the moment I'll write infinity or minus infinity. So that's all a vertical asymptote is, and oh my goodness, the language that we have to navigate in pre-calculus when we don't have limits is to say, oh, the graph gets vertical the closer you get to this line, or oh, look how high it goes up, right? We've ended that discussion, right? We've now phrased what a vertical asymptote is in this case. Questions about that? Five plus 1 over x. Oh, let's reset this, right? Can I just make it home? There we go. 5 plus 1 over x. We want to see where this goes. This seems to level out where? At 5, right? I want to talk about 1 over x first. And the limit. So now I'm going to talk about the limit as x tends to infinity of f of x. I want that to be L. Whew, I want to offer some extra credit. Can someone formulate what this means in words? That's the definition. You'll need to take a second, think about it very carefully. What does that mean in terms of maybe the skeptic? Somehow about making f of x some relation to L by doing something to x. I can make f something to L by making x something . All right, I'll open the floor. Anyone want to give it a shot?
So the limit as x approaching infinity of f of x can be arbitrarily close to L by making x as sufficiently large.
That is correct. That's absolutely right. That's absolutely right. So we can make f of x arbitrarily close to L by making x large enough This is clear with a 1 over x. The claim is that as x tends to infinity, what happens to 1 over x?
because tails goes on asymptote.
Yeah, so what is it?
0.
The limit is 0. Now, the lower level way, the level 1 way of saying this is, well, when you make x bigger and bigger and bigger, 1 over x gets smaller and smaller and smaller, right? When x is a million, 1 over a million is 0.00001. When x is 10 trillion, it's 1 over 0.000, right? The bigger you make x, the smaller 1 over x becomes. That's the lower level way of thinking about this, right? So the higher level way of thinking about it is to use the definition. Is to say that when the skeptic comes in and says, well, it's first of all just saying that I can make 1 over x as small as I want by taking x large enough. Right? That's the definition. Right? And so what that means in terms of the skeptic is the skeptic comes in and says, oh, no, I don't believe that. Right? And they say, well, you don't think it goes to 0? And then he says, no. I think we're on she now. She says, no. And then you say, so you think it stays away? And she says, yes, I do. And then you just prove her wrong. So that she is saying that, yo, I think that just 1 over x here. One over x. She says, I think it stays above 0.01. And you just need to go out far enough. How far do you think you need to go to get under 0.01? Past the 100. Past the 100, it's past 0.01. And we can adjust that, right? 100. 101. 0. 0.02. So past that, you're under that line. Right. And then she says, oh no, wait. I'm sorry. I think it stays 0.001 away, and then you just go out farther enough and it goes under. For every epsilon that's given, she can find an x so that way you're within epsilon of the number that she says, right? So for every epsilon greater than 0, there is an m that's large enough such that when x is bigger than that m, the distance from F to L is less than the number that she claimed was not possible. Right. So she gives an epsilon and says that, can you be within 0.001? And then you say, sure, if x is bigger than this really large number. That's the mathematical definition. Okay. So 1 over x goes to 0, and so that's a very easy proof. Someone gives an m, and then someone gives an epsilon, and then x is like 1 over epsilon. X needs to be bigger than 1 over epsilon. And so that's pretty straightforward to prove that by the definition. So we have a clear definition now about a horizontal asymptote. Of course, you can form an analogous definition for this. The limit as x goes to minus infinity of f of x, right, is equal to L. Please.
Wouldn't the definition be different? Because, you can, at least I think you can cross the ordinal classes.
Oh, sure, you can. So you can do something like this, right? So I said nothing about, there's nothing in the definition that I'm about to give, which I have not given yet.
Yeah.
But there's nothing that says that you can't cross it. So here's the graph. I'm going to call that L. y equals L, right? And so, I mean, who cares, right? So it's not about what happens early on, it's about what happens all the way down the line, right? So you can cross the line as often as you like, but it's about what happens as you move all the way down, either to the right or to the left. Is that okay? Yeah. So let's give the definition. So y equals L is a horizontal asymptote if the limit as x tends to infinity of f of x is equal to L, or the limit as x tends to minus infinity of f of x is equal to L. In words, what does that mean? That means exactly what we said in pre-calculus, that as you move all the way to the right, you're getting closer and closer to this number L, or as you're moving all the way to the left, you're getting closer and closer to this number L. Of course, we're saying this in a much more rigorous way, that I can make f as close to L as I like the farther I go out to the right, and I can make f of x as close to L as I like moving all the way to the left. That's all we're saying. Questions about that? So those are all the limits that we'll run into. I'm trying to figure out, there's nothing on the homework about infinite limits yet, but we'll give you some. And yeah, when we do that, we'll talk about some special types of limits. Okay, let's get to continuity. Continuity. Street version, no brakes, jumps, holes, none of that. No brakes or holes. Street version should be able to draw the graph without lifting a pencil. So the street version is the version you would tell somebody on the street. They come up to you and say, "Yo, my life is on the line. What does continuity mean?" And you say, that's what you tell that person, right? We want to formulate this mathematically. That means that if I have a function f, we're talking being continuous at a, right? That we're talking about not that, not continuous. Continuous?
No.
No. Continuous?
No.
No. So here's some situations where these are three functions that are not continuous at a particular point A. Right? So that when we define when we define continuity, then it's going to eliminate all three of those. We want to make sure that those three things don't happen. Right? Here's the definition. Definition. F is continuous this is like question number 3 or so on the test. Define continuity at a point A. F is continuous at x equals A if of the following are satisfied. This is hinted at on the homework. Number 1, I'm going to get rid of this. Why is this not continuous? It's a hole, and we just want to formulate what that means. There's a hole here, and so that means that there's nothing assigned to A. So I need f of A to exist. Right, so I need f of A to exist. F of A is defined. That gets rid of that problem. Please.
Isn't I mean, I know the last one isn't continuous, but isn't technically
Wait, where?
on the last one?
It is. It is defined on the last one. So this one satisfies this. That's perfectly okay. So this is not continuous for some other reason that I'm about to say. That's right. But yeah, so f of A is defined there. That's perfectly okay. Please.
Couldn't you just define it like in one like sentence saying that like the limit of A, I guess
The limit is x goes to A.
as x the limit as x goes to A, like as in like every point on the graph.
Yeah.
The left limit and the right limit are equal for like every point on the graph. For every x there is.
That was true of this one, right? The limit from, so this is L, right? The limit from the left is the same as the limit from the right. It's L.
Yeah.
Is that okay? Yeah, but for some reason, that's still not continuous. Okay, so good. These are great questions. So f of A is defined. Let me get rid of this one. What's wrong with this? There's a jump here. Looks like the limit from the left is not the same as the limit from the right. Looks like here, what happened?
So you have to make the limit as x goes to A f of x equals f of A.
That is the entire statement, and I'm simply breaking that into 3 statements. That's exactly correct. And so this particular issue here is that there is no limit. The limit doesn't exist today. So we need the limit as x goes to A of f of x to exist. That gets rid of that problem. Here I got a nice function, and it's like, yo, nice and continuous, aren't I? F of A is defined. I clearly got a limit. What's wrong with me? Well, this dot needs to be where? Right there, right? That the limit has to be the same as where the dot is, right? So the third and final condition is that the limit L and f of A better be the same. And as my brother just said, that's simply saying that the limit as x goes to A of f of x equals what? F of A. So some people like writing that one statement to be continuity. I will take that. When we in practice, we're going to check these 3 things, and on the homework, you just simply check these 3 things, right? Now the homework is kind of funky, you know. Someone wrote these problems and programmed it so that they give you a graph and they say which one of the following is violated on the homework, right? And so if you see this being violated, this supersedes this, right? So if a limit doesn't exist, then that violates and comes before this being violated. Because if there's no limit, then there's no way this could happen, right? Questions about this? The limit is x goes to A of f of x is equal to f of A, which means, again, the value has to be defined at A, the limit has to exist at A, and the limit and the value of the function have to be the same thing. f of x equals, it is 4 plus x if x is less than -1. If x is between -1 and 0, I would like to make it, let's say, 6 minus x. And then I want to make it x squared plus, let's do, you want to make it 2? No, I want to do something like, I want to make it 6. If 0 is less than x, which is less than, I'll use 2 there. And then I want to do, I want to make it x plus 10. Oh no, let's make it x plus 8. If x is bigger than 2. Please.
So when you did the original view graph to show how like we all violated the continuity.
Yeah.
I remember in pre-calc there's like they're like described as certain types of discontinuity.
Yeah.
I was wondering like if we still have to know that first.
Absolutely, yeah, that's right. So
because I know like one of them is the jump, one of them is the removable, one of them is the
absolutely, yeah, and that's certainly discussed in the homework. So yeah. So they are hopefully explanatory. Let's talk about the types of discontinuities, right? So when the limit from the left is not equal to the limit from the right, so this one is a jump for sure, right? You can fix this one. Currently there's a discontinuity, and you can remove the discontinuity by filling it in. So the street version is that holes are removable discontinuities, and then when you see a jump, when the limit from the left is not equal to the limit from the right, then it's called a jump discontinuity. Please. F is precisely what I want it to be. F is exactly what I want it to be. Questions about this? Please.
So can the jump also be called non-removable?
I don't know if I've heard this terminology.
Really?
Non-removable? Yes, sure, that's fine. We usually say jump or removable. But yeah, that's fine. Yeah, if you define non-removable, yeah, that's okay. Yeah, that's fine. That's fine. No, that's okay. That's good. Yeah.
So the one that just has the hole in it, like not the one that has like another defined value for A, is that one just considered non-removable, or is
Wait, which one?
the one that's like it goes through A, but there's like a hole, but there's no like other defined value for A.
So it looks like this.
No, not that one.
It's
Just the hole.
It's just the hole. You can fix that.
Okay, so is it?
So that one is removable, right? So if it's just the hole, that is removable.
So the one where it has a differently defined value for A.
That's also
Oh,
removable.
they're both removable.
Yeah, because you can fix it. You can either just move this in there, but if this wasn't here, you know what to put there in order to fix it.
Okay.
Yeah, so you can remove the discontinuity by fixing it in some way. Right? Please, thank you.
Are those the only two types of discontinuities
That we'll talk about, yeah. So there's some other ones that are just crazy, right? Like 1 over x squared at the origin. Right? That just goes to infinity. We don't have any. Please.
Are you okay with the term hole? You want to say removable?
We should use the definitions of the course. So yeah, it's removable. Yeah. So yeah, street version answers are only useful for yourself, right? So we should be using street versions on the test, right? So just, use the terminology. Math is a language, so we want to use the language. Where is f continuous? That's the question. I can also ask, is f continuous at -1?
Yes.
Because
Oh. No, no, no. Let's see.
you say no?
Yeah.
Because
Because they're at. It looks like a. Well, can a jump go down too? Because it looks like 4 is up and then.
you're saying there's space.
Yeah.
Okay, so
That's
good. No, excellent. That's excellent. So all I want to do is that. So what's great about mathematics? Oh my goodness. What's great about mathematics is that I could go to the inner caves of Mongolia and find a mathematician and ask her, what is continuity? And she would tell me precisely what I just told you the definition was. She would say exactly that or something equivalent to it. That the language across decades and across the world is exactly the same. The language may be different, but we're saying exactly the same. So when I say about f being continuous, once I make a definition and then I ask you why, then we can say the street version, which is what you said, but then we also now have to go back to the definition. What of those three things, if it's not continuous, is being violated?
It's the limits aren't equal.
That's exactly right. The limit from the left and the limit from the right are not the same, and so this violates number 2. That's excellent, right? And so all we're doing is translating from the words that make complete sense. He said that there seems to be a jump here, and mathematically you just want to say that the limit from the left and the limit from the right are not the same. Here's what you can write so that the grader is simply in love with you. Is f continuous at x equals -1? And we know that the grader can seem like a pain, right? But the grader wants to make sure that when you come across a really bad grader, that we don't run into any issues. Because the worst thing is when you know it and then you write something on the test and you get it wrong. That is just the worst, right? So we want to make sure that we're writing in a way that reflects our knowledge. Number 1, f of -1, is it defined?
Yes.
I believe so, right here, right? So f of -1 is 6 minus -1, it's 7. Number 2, does the limit as x tends to -1 of f of x, does that exist? I'll get the red marker out. The claim was that that's no. I need to see why. Well, it looks like the limit from the left and the limit from the right are not the same. The limit as x tends to -1, is that a question? Thank you. The limit as x tends to -1 of f of x is equal to, from the right, is equal to the limit as x tends to -1 from the right. From the right of -1, looks like 6 minus x, of 6 minus x, and that is 7. The limit as x tends to -1 from the left of f of x is equal to the limit as x tends to -1 from the left of, from the left we called it 4 plus x. Plugging in -1, that's 3. Find my cursor. Where'd you go? There you are. These are not equal. The limit from the left and the limit from the right are not the same, therefore there is no limit. By the definition of continuity, this is not continuous at -1. Yes, please.
Like if we wrote out what you just did, like just a second, if we knew that was the problem and just wrote out that the limit from the left equals this and the limit from the right equals this, and showed that they weren't equal,
Yeah,
can we just say just from there that it's not continuous?
that's correct. Absolutely. Absolutely. Yeah, so there's always some space that you have. I write everything out, but of course you can take whatever reasonable shortcuts there are. The only problem is what is reasonable, right? So that it's good that you're asking that clarifying question, right? So that it's clear what you can write and what you should not write. 2. Oh, let's do 0. 0? Do 0. Do 0. Is f continuous at 0? I think my computer's a little off. It's 9:10, yes? What time is it? Is it 9:10?
Yes.
Okay. We want to check 3 things for 0. Is f defined at 0?
Yes.
It is. F of 0 is 6. Perfect. Zero is 6 minus 0, right? 6 minus 0 equals 6. F of 0 is defined. Looks like this limit is going to work out. The limit as x tends to 0 from the right. The limit as x tends to 0 from the left. X tends to 0 from the right. We're talking about x squared plus 6. This is equal to the limit as x tends to 0 from the right of x squared plus 6, which is 6. This is equal to the limit as x tends to 0 from the left of 6 minus x, which is also 6. The limit is 6, so the limit exists. X tends to 0 of f of x is equal to 6. And then the final thing to check is that is f of a equal to L? Well, f of 0 is 6. That is also the limit. And therefore, all 3 of those things are true. F is continuous at 0. Questions about that? Please. Yeah, sure. And then 2. Is f continuous at 2? Yes? No? So you're talking about the first condition. You're talking about number 1? First condition? F of 2. What's f of 2? Is f continuous at 2?
No.
Question? Right, so f is not defined at 2. So f is not continuous at 2. Right. Okay, excellent. Okay, good. So we've got, I want to talk about one more thing about continuity, then we can talk about any issues about the homework, and it's the intermediate value theorem. The intermediate value theorem brings in the contacts continuity. I'm 5'10". At some point, I was like 2 feet tall. My daughter's 6. She's 4 feet tall now. Wow, she's 4 feet tall. It's crazy. Okay. Was there a time in which I was 3 feet tall? Was there a time in which I was 3.1474546 feet tall? Yes. All right. So between 2 feet tall and my height now, I was every height in between. Every single one. Why? Because height over time is continuous. Right? So every intermediate value, every value in between the lowest height and the highest height, I had to hit because height is continuous. That's all we're saying here. Right? So that a continuous function on a closed interval, right, hits every value between its minimum and maximum. Let f be continuous on the interval a to b, and that interval is closed. The temperature today started at 50 degrees. The high is going to be 95 or so. Will there be a time of the day where the temperature is 72 degrees? 12 degrees? Maybe, but we can't guarantee it, right? Right, so 85 degrees? For sure, right? Because what's the alternative? The alternative, if it's never 85, then what do you have to do with 85?
It will always be less than.
You have to skip over it, right? And if you skip over it, sounds like you're jumping, right? That's not okay with continuity. And that's what the proof is about. That when you want to prove this, then the way that you prove it by contradiction, right? The great skeptic comes in and says, yo, I think you can skip over a number, and then you say, well, wait, didn't we agree that f was continuous? And then he says, yes. And I said, well, then maybe you don't know what continuity means, right? And then he goes and sits down. Let f be continuous on a to b, then f attains a minimum, little m, and maximum, capital M. Now that actually has to be shown, right? But we're going to assume that for the moment. F has a maximum and minimum value on this, and so for every we can call this for every n between little m and capital M, there is a C such that f of C is equal to n. Right, so that's the mathematics of saying it. What does that mean? That means that if I draw something continuous, I start here, I can do all sorts of things, right? Here's A, here's B, here's the minimum, here's the maximum for every single n. For every single n between the minimum and the maximum, there is always at least one C. There's that C for this one. Oh, I got you. There's that C for this one. For this N, there's a C for that one. You have to hit for every value between little m and capital M, there is some X value associated with it. Okay. This is an existence theorem. It never tells you how to find C. It just tells you that C is there. And that's so purely mathematical. Existence theorems are so important in mathematics because we have mathematicians who actually want to find what C is. Right? And so they go about finding out what C is. So they need us theoreticians to say, yo, C is there. Now go look for it. Can you imagine going to look for something that's not there? That's crazy, right? If I want to go ahead and find the largest natural number, let's find it. I'm going to find the largest natural number. Let's call it n. N is the largest natural number. What happens when I square a natural number? Does it get bigger? It does get bigger, but I said that n was the largest one. So if n is the largest one, n squared can't be bigger, so they're the same. Well, if n is a natural number and n is equal to n squared, what does n have to be? 1. So 1 is the largest natural number. So all that all makes sense except for the assumption that there was a largest natural number. That was the only thing that I did wrong, was make a bad assumption. When you make bad assumptions and then start doing all these wonderful things from bad assumptions, you run into bad things. Right? So we just can't assume that things are there without understanding or showing that they are there before you start looking for them. Go ahead.
Go ahead. Never mind.
You okay?
Yeah.
Okay. So I guess that's my cue to close. So n is equal to n squared, so n is equal to 1. So this is useful as I finish for finding roots. And so if I have f of x is equal to, let's do x squared minus x plus, let's do this. F of x equals x cubed minus x plus 3. I'm going to show that f crosses the x-axis. Oh, this looks familiar now, right? How did I show f crosses the x-axis? Now, there are two ways to do this. You can either go ahead and set this equal to 0 and solve. Can't do that. You can make that extra credit if you want. There's a formula for cubics, I think. You could look it up, right? Or you could say, well, look, f of 0 is 3, right? F of negative 5 is negative 100. Oh,